will be coming in soon. Okay, everyone. So today, let me give an announcement first. I've had a lot of questions on homework 19 and 20, which you just turned in. So what I'm planning on doing is making a video of me going over homework 19 and 20, because a number of the problems had little tricks in it. And I want to make sure that you're understanding it. And I can't really take up lecture time. So one of you, could you remind me to say this at the end at 10:30 before we take the quiz? So I am going to go over homework 19 and 20 in a video and post it. Okay. So today our topic is frames. And I need to start out with some definitions first. So can everybody see this structure right here? This is called a truss. A truss has a bunch of members on it. And before I talk about a truss or a frame, I'm going to show you something. I'm going on to the module, which today and Thursday is frames. And does this look familiar to you guys? They're called erector sets. I remember having one when I was a kid. It's basically a flat metal bar that has a bunch of holes in it. So I could connect these bars to each other to make things. And I have a bunch of erector sets in the lab. And had we had a real lab in person, you would be building things with erector sets. So what I'm going to do is show you here. Can you notice this vertical member right here? Everybody can see it? It has 1, 2, 3, 4, 5 holes. Notice it's only connected on the end, right? And it's only connected on this end. This is called a two-force member because it only has forces on the end. And we don't see any forces on the end, but we know it's a connection, which means the reactions it supports are on the end. Look at this member now. This member has what, 5, 6, 7, 8, it looks like 9 holes. Again, it's only connected on the end. It's called a two-force member. Take a look at this member right here. It has 3, 4, 5, 6, 7, 8, 9 holes, and it's connected on the ends, but it's also connected somewhere else. It's called a three-force member. Okay, so the difference between when you call something a two-force member or a three-force member or a four-force member, it depends on how many connections or forces are applied at the points. If the connections are all, or the forces are only at the ends, it's called a two-force member. If they're in the middle, they're considered a multi-force member. And in this case, it's a three-force member. So now I'm going to go back and I'm going to not share. I'm going to stop sharing. And I'm going to show you this picture in the truss. You guys, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 members here. So you could imagine that if a construction crew was going to build this on the truck, 13 members would have to come on a huge flatbed because this may be a truss for a bridge. Okay. It says that each panel is 10 feet. Yeah, this is a huge thing. This is 40 feet long, and each one of these members is 10 feet. It's going to be arriving on a flatbed. Okay. So if there are all these members, these are all members. So Amani, I'm starting with you. If there are 13 members here, you could see that at point A, joint A, AB is connected to this. What kind of connection is that, Amani?
It looks like a bearing.
If they don't tell you what it is, your assumption is always a what?
A pin?
A pin.
Okay.
So since they didn't tell you a bearing, it's a pin. How about this one? Can you see there was rollers in it? Oh, I just gave it away.
You just get
It's a roller.
It's a roller.
Okay, it's a roller. So point A is member AB is connected to a pin at A and member AC by a pin. And at B, this joint pin is connecting members AB, BD, and BC. So Amani, and you notice there are two external forces at D and F. So all 13 of these members, what kind of force members are they?
Three.
2, 3, 4,
Three.
5, 6. Okay, try again. This is one member AB, and it
Oh,
is
two.
all what?
2?
Yes. These are all two force members because all the external forces and all the supports are only on the ends. David, you have a question on your face.
I'm just processing the vocabulary. Like there are points that have many forces at them, but we're talking about the members, not the points.
Right. So the
Okay.
points could have a zillion members at it. But in the end, even if there are a zillion forces, I could reduce them all to one. Right?
Okay.
Okay. So it's the location of where the forces are. So let's look at one of the problems we're going to see today. Your phone just came out. It's fine. It's no problem. Okay, one of the problems we're working on today is here. Can you guys see that?
Yeah.
Can everybody see that?
The dimensions are a little hard to make out, but yeah.
Okay, the dimensions, okay, it's hard to make out. Okay, so Angel,
Yes.
look at now here, I'm going to tell you that the member is not AB. It's not separate. The member that came on the truck is ABE. Actually, it's millimeters, so it didn't come on a flatbed. It come in our back of a car. So it's more like an erector set. So Angel, the member is ABE. That's one metal piece. It's connected at A by, what do you think?
Looks like a pen.
Right? How about at B
Also a pen.
and E?
Definitely a pen.
Okay. So what is this member called? A 2-force member, 3-force member, 4-force member?
Would this be a 2-force member like the last one?
No, it wouldn't, because it's connected at B2.
Oh,
This
okay.
member is connected at A, B, and E. So it's a
It's a 3-force member.
3-force member. Okay, Bond, what is member CEF? Again, this is one metal piece. What is it called?
Well, it looks like it's connected at point C and E, so I think it's a 2-force member.
Plus, there's a force at
Oh,
F. So
I
we
missed
look
that.
at the location of where forces are and connections, because a connection is really, in the end, just a force there, right? So
Right.
what member is it?
It's a 3-force member.
Okay, Colin, what about member BCD? Okay, Colin's not here. Daniel,
Wait, is there a pin joint I'm not seeing?
say it again.
How many
Well,
pieces
whoever-
are there?
Are we
How many-
talking about BCD right now, Jason?
B, C,
What do
D.
you-
I
what do-
thought was the same piece as all the way to F.
Okay, so
Oh no, there's
Uh,
a pin there.
And let's see.
Oh, there's a pin at C. Okay.
okay, I
never
have
mind.
no idea what you guys are talking about right
No, that's
now.
fine.
But let me
Well-
just say that if you're talking about BCD, I'm calling on someone. So Jason, was your question on ABE or CEF?
I wasn't clear on how many pieces in this assembly. It's very hard to see.
Okay, so I got it, broad scale. Thank you for
Broad scale.
clarifying. I didn't understand what your question was.
Yes.
So I'm going to tell you that ABE came as one piece. It's one piece of metal. CEF is one piece of metal. And BCD is one piece of metal. So sorry, when I did the truss, I first started with how many pieces there were. So sorry, I didn't do it here. So yes, there are 3 pieces separate. Thanks, Jason.
Mm-hmm.
Okay, so now Daniel C.
Yeah.
For BCD, is that a 2-force member, 3-force member, 4-force member?
I Can you move it a little bit more to the left?
Yes, oh, I'm so sorry.
Okay, I'm just going to take a shot in the dark here because from what I'm looking at, it looks like we have a roller, which will give us a force in the Y direction. And then
Correct.
we have, it looks like pins in
Yep,
B
there's
and
a
C.
pin at C and a pin at B.
Yeah,
So
so
ha-
I can see a 3 forces.
3 force member.
Yeah.
Okay. Are you guys comfortable? Let's look at the next problem we're going to work on. It may be today or it may be on Thursday. Let's look at this one. Okay. I think this picture is way better, right?
Yes.
Okay, good. Okay. So we're at Daniel Hall, Daniel H.
He has no power.
Okay. Danny. Danny?
Yes.
Okay. So let's look at BE. Does it look like it's one piece of metal?
Yes.
Okay. What is that? What number of force member is it? And why?
Three force,
Correct. Why?
because there's a tension from that weight,
Okay.
and then we have a pin at B
Yeah.
and a pin at E.
Great. 3 force member. Okay. Dave, what is A, B, C? We don't know it. That's not called anything. So let's call it F, where the pulley
F is the center of the pulley. Okay.
Yes.
So I think that's four
Correct.
force member.
Why? Why?
Pin at A, pin at B, pin at C, pin at F.
Yes. And now let me just, because you're talking about that, take a look at what's happening at A.
It's a
Even though,
rocker.
right. Even though we knew it was a pin right here, because it's a rocker, the rocker governs. Because if I did a free body diagram only of this piece, I would put a normal here, and then I would put a force in the X and the Y here at the pin, and I would find out that the pin doesn't have a Y. That's very important, you guys, because we have to learn how to simplify these problems because they're too intense. So let's do it. I'm going to say it again. If I did a free body diagram only of, let me just make sure you could see it, only of this piece, I would have a normal right here, and I would have a force, what's that, A? I would have an AX, up, AY, and an AX here. And when I do a free body diagram of this and then do the equilibrium equations, this drops out. And AX turns out to be what, Dave?
AX would be negative. It would be the reverse of the normal.
The reverse normal.
Yeah.
So that's why it's kind of like when you have a rope and you have a weight on it, and you know this weight is going down. We have already simplified this problem and said the tension that's here is equal to the weight. Because what we did is we drew a free body diagram of this point with the weight going down and the tension going up. And we did sum of the forces in the Y equal T minus W equals 0 and T equals W. We simplified it. It's the same exact thing of this, where I'm looking at this body, and because there's a normal here, I know AY is 0 and AX is only N. So even though when we look at this member A, B, C, F, we think A is a pin, we look closer at where this connection is, we know that it really only takes a normal.
Why is AX negative?
Because foolishly, maybe, I don't know if foolishly is the right word. It's not really foolish because I could draw it whatever way I want. I drew the AX going in this direction, right? So because I drew it to the right, AX is negative on this thing, right? It actually is going like this on this thing. So that means where AB is, it goes this way.
John, I still have a question. Can we move over to the member
Jason,
AB?
I want to come,
Oh.
Jason, could you remind me to come back to that question? Because I did notice some people are putting forces in wrong directions. And we're going to look at that a lot today. And then could you remind me to come back to this, Jason?
I completely dropped out for like,
Okay, just
20
remind me to come back to this,
yep,
okay?
can do.
Because of a reason. Dave?
Okay, can we scoot the picture over so we can see that whole member again?
Yeah.
Yeah. So we're calling ABCF 4 force
A
member.
4 force member. It's written like this, 4 dash force member.
But my question is this: at things like pins,
Yes,
they have 2 forces at least.
correct. Okay, I hope everybody's listening because this is all good things that people are bringing up. Even though there could be, like I said, okay, okay, you know how in the English dictionary, one word can mean many things?
Is that what we're doing?
Shit.
It's just a different use
Shit.
of the word. Okay.
Yes, shit could mean shit, poop,
Oh,
or
boy.
it can mean shit, a saying.
Uh-huh.
The word force, we know, means a load. But in terms of members, force acts as an adjective. If you saw it in the dictionary, it would say force, noun, load. And then it would say force, adjective, describing a member.
Or it means coerce
location.
people. All right.
It's the location.
So, okay. So would it
So-
be sufficient to say it's a 4 connection member?
For us, maybe yes, but it's not technically correct. That's not how it's called. It's called as a 4 force member.
Okay. So it
Or
is just
we
a
have
different
to-
use
we
of
have
the
to
word.
call it a 4 force member.
Okay.
And it may not be a 4 connection member. So let me go on to this for a minute. Even though B has a BX and BY, we could really take the resultant of that, and there's really only one force there.
Okay.
matter
Okay.
how
Yeah.
Let me keep going. No matter how many forces are at a point, I could find the resultant, and it's really one force. But the adjective for describing members really have to do with how many locations on a member are there forces. And there are 4 locations. And the reason why I think the word location is better than connection is look at this problem here. This is a member CDE. There are only 2 connections, but there are 3 points where there are forces, and it's called a 3 force member.
I got it. So yeah, that might be a good way to say it. It's points with forces.
It's the location. How many locations?
Okay. Okay. That
Or
helps.
how
Thank
many
you.
points?
All right.
Okay. Now, if we could also call a 3 force member or a 4 force member a multi-force member. Okay, because it's more than 2. Multi for us would probably mean 2, but something is either a 2 force member. I guess it could be, if it's cantilevered, well, if it's cantilevered, there's going to be a load on the end. Things are either a 2 force member or a multi-force member. And if they're a multi-force member, they can be 3, 4, or 5. So let's look at this. Let's say there was a distributed load here. I have no idea what kind of member it would be called. It's not a 2. It's not a 3. I probably would just call it a multi-force member. Okay. Everybody good?
Yeah, great question.
Okay, so now let's go back to this one. And Dave, I'm not sure if you answered or not, but you spoke a lot. So we're going to David.
That's fine.
What is CD?
CD's a 2 force member.
Right. So I guess a good question would be, how many locations are there forces? How many? There are 2. So it's a 2 force member. What if I did this and I put a distributed load on here? Is it still a 2 force member, David?
It's a multi-force.
It's a multi-force member. And I guess we could take the distributed load, right? And make an equivalent point load. And then what is it called, David?
A 3 force member.
Right. Okay, here. David, I'm going to give you even a more. Well, let's move on to Edgar. Edgar, so everybody gets a chance. Edgar, I'm going to give you a very complicated problem.
Damn. All right.
Okay. Can I take this piece of metal, pull it off, and instead put another piece of metal that's like this that connects at CD? Think about it.
So you're saying you want to remove that?
I want to remove CD and instead, by accident, the contractor in the flatbed of the truck didn't bring me a CD, but by accident gave me a diagonal, gave me this. Can I say, okay, no problem. I'm not going to fire you.
Put it over to the right, Joanne.
Oh, thank you. I'm not going to get rid. I can't. An engineer can't fire a contractor. We could talk about that too. I can't even tell a contractor what to do. Okay. Anyway, can I, Edgar, put this on instead of this?
I mean, you can, but if that thing's gonna be better, that's debatable.
Well, I guess I'm asking you a question. Is this one with the elbow better?
I feel like the one with the elbow's better because of the stability and how the force at the junctions or it's gonna be applied.
Okay,
'Cause-
so now that's maybe our intuitive question, our intuitive answer, but now let's put on our statics hat. I have to find the reactions at C and I have to find the reactions at D, right?
Right.
Whether this is here or this is here or this is here, it's still the same mathematical calculations. So therefore, I can replace this angle bracket with this. So why the hell would they do that? Because certainly this is more money because it has more material. It weighs more, so it costs more in fuel. Why would I put this on? Anybody have a guess?
Because it allows flexing.
No, has nothing to do with engineering.
Because it looks pretty.
It looks pretty. It's aesthetically pleasing. That's it. Or maybe another reason, somebody had this free in their garage. And it was going to cost more money to get this, even though it weighs less and costs less to move. So, David, you said this is a 2-force member, right?
Yeah.
Okay, good. All right, how is everyone? Can you distinguish between 2 and 3-force members? So I think the first thing I would do is say, how many locations on this member are there forces or connections? And that determines how many force members. Okay, so now I want to go back to my truss. The way you distinguish between a truss and a frame is that a truss, somebody want to take a guess? Oh, and Edgar, it's totally fine. You got the answer wrong. It's new stuff. Don't
Yeah,
worry.
I mean, it's interesting how in engineering you have to do stuff to please your eyes and not actually just to fulfill the requirements.
That's correct. And architects want to please their eyes all the time, and they couldn't care a lick about the, well, I shouldn't say that. But engineers and architects work together, at least in civil, not in mechanical. Okay, so here, where are we? Elizabeth? Is Elizabeth here? Okay, Eric?
Good morning.
Eric, hey, how you doing? So just in case you got here late, this is called a truss, and every one of these members are separate. So what kind of members are in a truss?
2-force or two?
Two force members. So trusses only have 2 force members.
Okay.
Okay. Once a structure has 1 multi-force member, it's now called a frame.
Okay.
Got it, everybody? Okay. Today we're doing frames. And to tell you the truth, you know how to do every one of these problems anyway. Already. I guess since we're talking about the 2 and the 3 force members, let me show you the trick now. Okay. No, I'm not going to show you the trick yet. Okay, we're going to do this problem now. What I want you to do, and I probably should have told you to print this out beforehand, but it's a bunch of lines. You'll be able to do it really quick. I want you to draw a free body diagram. I got to pull this up. Oh, I'll go back down so you can see it better. But I want you to draw a free body diagram of every, so, okay, well, is this a frame? Where am I? Hang on. Gerardo, is this a frame or a truss?
It's a frame
Why?
because it has more than two forces.
It has at least one
It's multi-force.
one multi-force member. Okay. So what I want you to do is I want you to draw a free body diagram of all three of these members, and I want you to draw a free body diagram of the total structure itself removed from its main supports. Okay? Go for it. And why don't we do it in meters rather than millimeters? So just call well, actually I drew it in millimeters already, so all right, millimeters. Okay, hang on a second. And now I'm going to zoom in so you could see this thing better. Actually, you know what? My other copy is way better. Are you getting? Oh, my mom had vertigo yesterday. But I'm giving you vertigo now.
Yeah, the shaky cam is really.
I'm
It's
sorry.
really fun. It adds a lot.
Okay, hang on. Just,
I actually got vertigo.
Oh, Eric? No, Daniel.
Yeah. I had a bad case of vertigo earlier this semester.
Oh, really?
Yeah.
Okay. All right. Yeah, I should take a chill pill before I teach.
Or just stabilize
great.
your rig.
Well, it's stabilized. What? Say it again?
Stabilize your camera rig.
Yeah, well, it's stabilized. I just keep moving it. Can't sit still. I'll stop kicking the table.
A
Okay,
Joanne,
draw all the free body diagrams.
of every part, right? And then one of it all together.
Right. So of every member, let's not call it a part. Let's call it a member, because in trusses and in frames, they use the word member.
The only external force is at F, right?
Correct.
The lines are kind of blurry around B in the
Yes.
corner there, but
Yes,
it's just
correct.
okay. Thanks.
The only external force is 150. And all
Okay.
these dimensions are 100 millimeters except for CD. CD is 200. Oh, see, I moved the camera again. You done yet? Just kidding. Okay, you guys, you should be finished by now. You got to go a little quicker. You got to go quicker. And if it means that you might just need to practice more. Okay, but they're all pins. Okay, so now let's see. Up to. Okay, we're up to Hyoji. Okay, I'm going to pull this back now so I could see my members here. Okay. Okay, Isaac. So let's do ABE.
Do ABE?
Yeah.
Like what forces are
What
on
forces do I have to draw here?
it? You have you have BX, BY. You have a normal at A.
Okay, wait, BX, BY.
You have a normal at A.
Okay, well, take a look at A again. What kind of connection is that?
That's a pin. So you
A
have a
pin.
normal.
So I have
AX
what? AX and
AX.
AY.
Normal. Yeah.
Okay, and then what about E?
EX, EY.
Right. And I tend to draw them all positive the first time. Okay, Jack. Jack, you here?
Yeah, hello.
Okay, great. Jack, let's do now CEF. What do I draw?
So at E, there should be in the X and the Y because that's a pin.
Great. Okay, so now Jack, you got the tricky question. And this is something that I wanted to talk more about.
Yeah.
How do I draw the two forces, EX and EY at E? And a number of you got it wrong on the quiz, but I know you're going to redo the quiz, so you'll get some points back. Jack?
I would assume you just put it slightly to the side, but I'm not positive.
Oh, I mean, which direction? Does EX go to the positive or do I draw it to the negative? Okay, before you answer, let me ask you this other question. If I connect member CEF with ABE at E, if I connect these two at E, they're connected still, wouldn't the EX-EY be an internal force? And I wouldn't draw it.
Oh yeah, huh.
So that means think about it, if I'm putting these two together, how do I get the EX and EY to cancel?
I didn't think about that.
Okay, well now you're thinking about it. So how would you draw EX?
To the left.
Yes.
And then EY down.
Yes. Okay. So you have to think about these two have to be drawn in opposite directions because if you put them together, they cancel out. So check your quiz. Even if you saw, oh, I got a 9 on the quiz, great. I don't have to read Joanne's comments. Read the comments. Jason?
So would it sorry,
Okay.
so would it
No,
be
it's okay.
the same
Keep going. Keep going, Jack.
for like C? Would it be the same idea?
Yes, but in this case, this is the first time we're drawing C, so we could draw whatever the hell we want.
Yeah, I would just draw it normally, positive in both directions.
CX, CY, and what else do you have to put on here?
And then just the 150 newtons.
Right. Okay, Jason, you're up next. Do BCD. What about B?
Well, BCD has one going, I'm going to call it BY, and it's pointing down.
Great.
And BX, and it's pointing to the left.
Right.
And then it has, wait, I need to reference your choices on C.
Correct.
It looks like, yes. Okay, so C is going to have 1 going down and 1 going to the left. Yeah.
Right.
C, Y going down. And then D is just going to have 1 going up, and we'll call that dy.
Great. We could call it dy, or we could call it normal. Would you rather? I think I have a tendency to call it normal because I know if I get a negative in a normal, I made a mathematical error,
Okay.
right? So
we'll
I
go
tend
with
to call it a normal so that it's another way I could do my check. Okay. Okay, Jason Lee. Now let's do the whole structure.
Yes.
So tell me what forces should I draw?
So you're going to draw the AYAX.
Okay, now this is a little confusing. How do I draw A here? Do I draw it the same way as the other A, or do I draw it opposite? Everybody should think
same.
about it. What?
The same?
Yes, excellent. The same. It's the same point on the same member.
Yeah.
Okay, what else, Jason?
And then you're going to skip B because it's internal. Then skip E, skip C. So you're going to end up with normal.
Right?
And the force.
Force. Is everybody okay with A being the same and the normal being the same? So in the end, we have 1, 2, 3, 4 free body diagrams. Everybody okay? Questions? Remember, you have to have the axis. You don't want any points taken off. And you want to make sure you have the distances. Why, Jordan, why do I need all these distances on here?
It's important information to show, it's like relevant to the forces and the moments.
Right, it's relevant to the moment, certainly. The main reason is you're going to calculate moments, you need distances. But second, you're drawing a free body diagram. This guy's a body, he has a length, you got to give him a length. Okay, any questions on this?
I have a couple.
Yeah, Isaac?
So first one is, so it's okay if we're drawing a bunch of free body diagrams, it's okay to draw the axes just once?
Sure.
Okay.
But if they're on different pages, give me another axis. Did everybody hear that? If all the free body diagrams are together, you could draw one axis, but if they're on different pages, in fact, you probably want to even label these free body diagrams, C, E, F, B, C, B, C, E, free body diagram, because I'm going to have to do equilibrium equations at some point, right? This is free body diagram A, B, E, and free body diagram B, C, D. Remember, I want things to be neat and clear. If you need to write nine equations, you need to tell me which free body diagram the equation's coming from. So either you draw a free body diagram and you put all the equations under it, and then draw the next free body diagram and do all the equations, or you do all the free body diagrams and label them, so then you say free body diagram ABC, and then you show me the equations. I don't want somebody to be trying to figure out which free body diagrams you're using. But today we're not concentrating on the equations, we're just concentrating on the free body diagrams. And let me just interject because I might forget at the end. I had a number of homework 19 and 20 questions. And since I can't really discuss it in the time of the lecture, because we only have 3 hours a week, what I'm going to do is do a video, a side Zoom video explaining how I did all the question and the problems and address each of the questions, and then I'll post it. Okay, there are a few people with a question.
I had one more question.
Yeah, Isaac.
So you've got free body diagram ABE and another one for CEF. In both of them, you have EYEX. But the directions are reversed. Is it basically okay to call those the same thing because they're in different free body diagrams?
You definitely want to, because take a look at this. how many unknowns do we have here? I'll do it in a different color. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 unknowns in this problem, right? It's a lot, right? We want to make sure that, so for one, we don't want to introduce another 2 unknowns. And when you use different variables, that's what in essence you're doing. If you call something a different variable, you're telling the reader that it has a different value. You know, unless you say, if you call this EX and you call this EX prime, and then you say it's EX is equal to EX prime, great, but then you're having another equation you have to write up here, right? So if these forces, what this member experiences here at E is equal and opposite what this member experiences at E. It's the same value.
It's a really
Okay.
good question
Yeah,
because it's not the same vector. I refuse.
right. It is not the same vector, but it has the same value of magnitude.
The direction was just dependent on which one you did first, right? You
That's
happened
right.
to draw that one first so that you default to positive, and then you drew another diagram, so you had to reverse it.
That's right.
So my question was like, if you did, I don't know, B, C, D first, you would have the B's and C's up and right on that
Correct.
one, and then
Yeah.
flip them on the other ones. And that's
Right.
acceptable. That's okay.
It's totally acceptable. You
Okay,
get to decide. You get, in fact, if we only had one member, you get to decide whatever way you want to put the arrow. You choose, because your solution in the end is the free body diagram and what the values are at the end. You could choose. So whichever you choose one, you just have to remember that if 2 bodies are connecting, you got to show it equal and opposite. And we did look at one class problem in the past. And then on the quiz that you did the other day, it had it, but you obviously didn't, everybody hadn't processed that yet. So sorry, but you're going to have it now. Okay, so now I want to go to the other problem we're going to work on, this one. And let's see. I don't know how bad the copy is. Let's see. How does that look to you? Is it bad or is it okay?
It's legible, but a little fuzzy.
Yeah, I think that's
At
actually
least
the camera
it's
focus.
at least
Is he
defined.
No, it's
zoomed
not
in?
the camera. Well, tell me now, is it blurry?
That one's better.
Okay,
That one's better, yeah.
yeah. Okay, so it may be the camera, but the camera that took the photo of the good one that came out bad. Okay, all right, so now I want the same thing. I want you to draw a free body diagram of this member. I want you to draw a free body diagram of this member. I want you to draw a free body diagram of this member. And I want you to draw a free body diagram of the pulley. And the total thing. So you're going to have, I'm going to move it up for a minute. You're going to have 5 free body diagrams. Member BE, member ABCF, and member CD, the pulley, and the whole thing with the pulley. So do you prefer me to leave it like this, or do you want me to zoom in? What do you want? Nobody's saying anything, so I'm just going to leave it this way then.
Actually, Joanne, could you focus it on the picture?
Yeah, I don't know how to focus.
Or not focus it, but
How do
just
you focus an iPhone? I have no idea.
then you just tap the screen.
Oh. Okay. All right. So if you want me, I could just, is that better, Angel? You're the only one expressed an opinion, so I'll just give it to you.
Yeah, that looks good. Thank you.
So there's,
So Joanne, a side note on
there's 3 members, a pulley, and the whole structure. Okay, who's the side note? Tim?
yeah, on the when you were talking about, like if you have BX and you draw the arrows the opposite way, that's also a good way of thinking about if you have equal and opposite on two different free body diagrams, it's going to be an internal force in the system.
Correct.
So all
And
internal
it's
forces
more-
in the system should be balanced out in that way.
Right. And it's better to say the opposite of what you said. When the problem is internal, when the two things are connected, it's internal, so it has to cancel it out.
Mhm.
Not because it cancels it out, it's internal.
Got it.
Two things are connected still, the forces inside are internal, and therefore they can't be shown.
Yeah, got it. Cool.
Joanne, I had a quick question about the previous picture.
Yeah.
I think I missed it, but did you say, is there a normal force at A, or is that part of your reaction?
It's part of the reaction.
Okay.
Let me just check because I'm thinking I know where A is. Yeah, at A, it is only a reaction at the support, which is a pin. So it's an X and Y.
So whenever there's a pin,
Because in a way, the AY is covering for the normal.
yeah, okay, thank you.
Okay.
The pulley is another one, right? Are we doing a separate
Separate free body
for the?
diagram for the pulley.
Got it. Okay, yeah, thanks.
I really love frame problems.
Yeah, this one's messing with me. I keep trying to imagine.
Yeah, Joanne, you seem very excited about this
Oh.
section.
Yeah. I feel like, it introduces a new topic, frames. Oh, we're going to have to learn this big old thing, but it's really like, this stuff already. There's just some little things that you need to know. But it's cool because it's a lot of frame problems is figuring out which equation should I do to get one unknown in it, And I like drawing and I like puzzles.
And we decided to call the pin in the center of the pulley, name it something, right? We called it F.
I think you mean this one right here?
In the center of the pulley?
Oh, I'm sorry. Yes, let's call it F.
Okay. Because you need that, right? You have to, well, I don't know. We'll
Yeah,
go
we
over
should
it.
have it. We should have it called something.
And is the 1 foot next to the pulley representing its radius?
Correct. Could you look, you see below Angel, it shows 2.
Oh, that makes sense.
Here, so that's a confirmation, yeah.
Okay,
But
thank
yeah, it's hard to see.
A can move up and down, yeah.
Say it again.
The member A, B, C, F can
A could move a little
translate.
bit like this. Yeah, it allows a little bit of movement.
But only so much because it's fixed.
It's not fixed here. It's fixed at these two places.
Right.
Right. I like that you think about it physically. Okay, everybody got them all? Okay, I'm going to count down. When I get to 1, 10, 9,
Okay.
8,
All those
7,
cooking shows.
6, 5, 4, 3, 2, 1. Okay. So, Jordan, Cody, Laura, which member do you want to do first?
Either one, it doesn't matter.
Okay. BE.
Okay, so there's EY.
Right.
And EX.
Right.
BY and BX.
Okay, anything else?
No.
Take a look closer at the picture.
Oh, wait, and the force and the tension.
Tension, right. And why are we calling it T?
Because it's the same.
It's a tension. Okay, now in this case, we're calling it tension, but it actually in the end is the weight, right? Let's, you know what? We were doing free body diagrams, practicing that we didn't really read the words. Let's look at the words for a minute. The suspended cylinder has a weight of 80 pounds. So let's not call it T, okay? Let's just call it 80 pounds.
Okay.
So we know it's not an unknown. Sorry, I didn't read the words first. Okay, Liam.
What isn't it? W?
Yeah, we could call it W, but I'm going to put 80 pounds because then I know it's, I know the number.
Okay.
Sometimes when I'm doing a problem, if I see a variable, I think it's an unknown. You know, so sometimes I try not to put the unknown, the variable in. Okay, Liam, Luis. Mackenzie. Oh boy. Maria.
Yes, ma'am.
Do A, B, C, D. Sorry, A, B, C, F.
Okay. So at A, there's AX. At B, there's BX and
Wait,
BY.
at A is AX, right? And why is it AX?
Because it's a rocker, so it only
It's
has
a normal, right? Could we call it an N instead? For the same reason before we called it an N, because if we get a negative, we know we made a math mistake. It's just another way to check. Okay, what else?
Okay, so then at B, we have BX and BY, and BY is going to be facing down,
Right,
and BX is going to be facing in the negative direction.
right.
And then at C, we have CX and CY.
Okay,
And then at F, we also have FX and FY.
right. Okay, so I'm going to do this. Sometimes I like to do this so that I don't feel like these forces run into each other. So this is free body diagram BE. This is free body diagram A, B, C, F.
So the normal,
Okay.
we just call it a normal when it doesn't have any other reactions in any other direction.
Right.
Okay.
Well, yeah, and it's also, it is a normal, it's just touching. It's, if you look at the picture, there's only a touching here.
Yeah.
There's
It's
no connection. It's just touching the wall, so it's a normal.
just a reaction there, like AX, but it's better if I call it the normal.
I would call it a normal. You could call it AX. It's totally fine. The reason I call it a normal is because if I get a negative at the end for the normal, it's a way for me to check my work because I know I could never get a negative normal. We know that it has to be going this way because if I'm drawing a free body diagram of this wall is pushing in that direction.
That makes sense.
But you could call it AX if you want.
Okay.
But I just like to have a lot of checks.
Okay.
Okay. Marcine.
Yeah.
Okay, Marcine, sorry, I skipped you by accident. CD, what do I draw on here?
You have your dy, dx. You can draw them in the positive if you want.
Okay, hang on a second. Let me just put these there. What's this B? Okay, say it again. D?
Your
I could
dx.
right, I could put them in the positive. Good.
And on your C, you're going to have to put them in your negative
Right,
directions.
I have to do it the opposite. Okay, anything else on here? No. So free body diagram DC. Okay. Okay, Marcy, Maria, Matthew. Now let's do a free body diagram of the whole structure.
Okay.
So what do I have to draw?
Start with E.
Oh,
which
actually, I
is
didn't
how-
do the pulley yet, but that's okay. Do the whole structure, Matthew.
Okay. So E, like we have in our other free body, we would have EX and EY.
And which way do they go?
EX would be going to the right and EY would be going up.
Right. So it's the same, right? Because this is the reaction at point E and it's still the same reaction. Okay, what else?
B would be all internal.
Right. So I don't draw
So then
anything.
we'd go to A.
Okay.
A would just be the normal force going to the right.
Right.
And then going down to D, that would be the dx going to the right, dy going up.
Great. And
C is all internal.
right.
F would be internal.
Correct.
Yeah.
Great.
Okay. So then we would just have the tension, which would just be going down.
Right. Excellent. So free body diagram total. Okay, and now let's do the free body diagram of the pulley.
I'm
So-
confused about how come the F forces are internal.
Because it's still connected. Remember, whenever things are connected, they're internal. It's not until you pull them apart that they become external. The pulley is still connected to this member here. It's connected, it's internal.
Okay.
Okay.
So there's
Now, but I can say though, Maria, if I drew a free body diagram, well, we can do it. Let's just do it. E, can everybody see what I'm doing? Yeah. A, E, C.
Joanne, did you pin the proper video this time? Did we figure this out?
I think I did. I pinned this thing.
Okay. We'll find out.
So I think I did. I called the C, not important. So let's say I do the free body diagram of BE. Okay, well, who's next? Myra?
Yes.
Myra, if I had a free body diagram of this and I pulled the pulley off, what would be in my free body diagram?
All the other ones.
Okay, so
the
let's
normal.
do it. dx, dy, the normal, ex, ey. What else? Oh, what would I have here?
So the tension would be off of the B.
Excellent. This is where my tension would be, and I know the radius here is 1, so this is 1 foot. Okay, what else?
And
great question, Maria.
that's it.
One more. Remember, I separated member A, B, C, F from the pulley. So how do I?
So now it would have a FX and FY.
Right. Okay. So now Miles is next. Miles, you here?
Yeah.
Okay, Miles, do the pulley for me now. Oh, wait, Maria, does that answer your question?
So in the other one, can you just show the other one? We have
Yeah.
the book on it. Oh, okay, I see. Yes. Okay. So then that means it's just the tension is just down because it's still connected. Like at so
Well, on this one, I only see the tension here because I don't have the pulley. It could only show the X and Y force and the F.
and we draw the tension like we don't do two tensions like one.
No, because this tension is off the pulley and I'm not drawing the pulley. Great questions.
Okay.
And it'll make sense now. Once Miles tells us what I have to draw on the free body diagram here.
Okay, thanks.
Miles?
Yeah, so I'm thinking you're gonna have two tension forces, or not two unique tension forces, but like one down and one to the
Right,
left.
so the 80 pounds is going to be here. Oh, and actually, shoot, this T is 80 pounds, right? What the hell am I doing putting a T? It makes it like there's another unknown. It's 80 pounds. So there would be an 80 pounds here and then 80 pounds here. Does that make sense? Because, and then what else would I have, Miles? One couple more?
Then you would have an FY and FX.
And which direction would they go in?
The opposite direction that you drew on ABC.
Right.
Move the paper left, please.
Say it again.
Move paper left, please.
Yes.
Thank you.
Does that make sense? So now, Maria, back to your question. If I take this pulley and I put it on this member, the FX and FY drop out, and the 80 pounds right here drops out, and that's all it leaves me is no FX, no FY, and internal FX, FY, internal 80 pounds here, but it leaves the 80 pounds there. So what we're doing is we're taking two free body diagrams and we're putting them together.
Now, when we calculate FX and FY, at least in terms of the pulley, we would expect to get negative values for both of them.
Right. You see that?
Correct.
So probably had I been thinking, I probably would have put FX and FY the other way in this one, but I did this one first, right? But it doesn't matter. You're just going to get negatives. But negatives are confusing sometimes.
So when I look at this frame and I replace the 90-degree members with straight lengths just to simplify it for myself, I can't convince myself that this thing is stable.
Okay, well, we'll talk
given the
about that
support
another time then.
at A.
Okay.
Uh-huh.
Okay, so now, do I want to go to the next step?
I see a quadrilateral.
I think I want to go to the next step. So you will start the quiz in person, but then it's going to go over a little. Or should I just stop? I think I should stop. I'm going to stop. But you guys, make sure you have these sheets with you on Thursday. Okay? So what we looked at is now we know the names of members. There are 2 force members if there are 2 locations that forces are on. There are 3 force members if there are 3 locations. They're multi-force members as long as they have 3 or more on it, 3 or more locations. Okay?
What was the trick? Did you show us the trick?
No, I didn't show you the trick yet. We'll do that on Thursday. Okay? Because I think that trick is going to be a 15-minute discussion. It's too long. Okay, and it's not really a trick, but okay. And then hopefully you're comfortable with the whole idea of putting these free body diagrams together and separate, whether when they're still together, the forces are internal. It's not until you separate them that they become external. Okay. All right. So let's go to the quiz. So I'm going to, I guess maybe I'll.
I mean, it's unlocked and everything. We can see the quiz.
I know, but I want to, yeah, I'm trying to manage both things right now. Okay. All right. So everyone, I guess you could probably see it better when it's shared, huh? Can you see it better when it's shared? Nobody's
Like
answering me.
screen share?
All right, nobody's answering. So I'm just going to talk about it. So this is called a 1 equation only quiz. And I know when we did homeworks 19 and 20, you looked for equations that only had 1 unknown in it. Okay, so let's take a for the static structure, which happens to be a truss, but it has nothing to do with a truss right now. To the right, treat the structure as 1 body. So basically I have this 1 body. And realistically, the reason why we do trusses is because it's lighter. Everybody look up here at my fingers. All these members have air in here. I could have replaced this whole truss with this plate, this huge plate, and it would have done the same thing, but it would have been heavier. And that means more money, more expensive to build it and such. So this is a truss, but you're treating it as 1 body. So assume, make believe it's 1 big old body here, A, B, C, D, E, A, all the way through to A. There is a connection at A, and there's a connection at E, and there's only 1 external load. Okay. So these are the only forces. There's only, oh, I'm sorry. And there's one at F. Am I blind? Okay. So there's a 100-pound force at B. There's a 200-pound force at B. And then there are reactions at support A and there's reactions at support E. So the first thing I want you to do is create a table showing all the known and unknown magnitude and directions of the forces and moments. How many unknowns are there? How many equations do you need? And how many free body diagrams are needed? And that's all worth 2 points. Okay, next, I want you to draw a free body diagram of the whole structure. And like I said, you don't have to draw all these members. You could just color it all in. It's basically a huge body that has 2 external forces and 2 things here. And then 3, 4, and 5, I'm asking you, read the question in detail. Use only one equation to determine one of the reactions. Use only one equation to determine the reactions. So make sure you read the whole question. Okay? Okay, you could go. So now I think what I'll do is you could pull it up, but I'll also share the screen. I have to stop sharing and then share it another way.